everyone, and welcome back to our NACE Calgary webinar series after a brief hiatus. I'm Abby Amu, Vice Chair of Programs for NACE Calgary. Today I have the pleasure of presenting a webinar presented by Bruce Levan and hosted by Brett Johnson on October 7th. Bruce has a long history of providing failure analysis and consulting services for welding and inspection to the oil and gas industry throughout the world, including Canada, North Africa, and the Middle East. Bruce graduated from Northern College with a degree in metallurgical engineering with a specialization in welding engineering technology. He worked for Ontario Hydro, where he inspected boilers and turbines and was responsible for weld repairs on nuclear reactors. He has since built his own consulting service as Levan Engineering Limited. We were talking with Bruce about presenting for our program for over a year, so we are very excited to be able to have him on our channel. Of course, none of what we do at NACE Calgary would be possible without our annual sponsors. Their contributions allow us to be able to provide this webinar series to our membership at no charge. Today, I'd like to highlight one of our gold sponsors, OnStream Pipeline Inspection, a member of the Mistrust Group. OnStream has been a huge long-term supporter of NACE Calgary for over a decade. They specialize in small diameter MFL inspection tools that are free-swimming or tethered. Their newest line of tools, the TriStream MFL, brings ultra-high resolution capabilities using triaxial technology to capture dimensions in the axial, radial, and circumferential directions. Research has shown that single vector MFL tools can only capture about 80% of the defect's shape, while using all three vectors can enable you to derive 99% of the information about a defect. Triaxial sensors, combined with state-of-the-art algorithm technology, reduce uncertainty in defect shape, which provides enhanced input into the sizing models and ultimately improves accuracy, which reduces both pipeline risk and integrity program costs. And of course, all our other annual sponsors are a huge reason why we can do what we do. Our sponsors help fund several initiatives that NACE Calgary takes on to promote the knowledge of corrosion, sustainability, and asset integrity to our industry and the next generation of engineers. To each one of our sponsors, we thank you for your continued support. Now, on this presentation, there was a little bit of technical difficulties in terms of when the screen share was enabled and when the actual recording started. So we're going to be coming into this presentation a little bit, maybe 5 minutes in. So I'm going to make sure that we put the slide that was missed and have a little bit of an explanation as to what that slide was showing.
The unfortunate thing is now you've cut a hole in the pressure vessel or the pipe, and you got to do the repair. You got to submit the paperwork to ABSA. You got to do the heat treatment, the inspection. So it's a lot cheaper to do an in-situ replica, which is what this shows. All these glass slides here are cellulose acetate that's been mounted on a glass slide. And so I polish the surface on the pressure vessel or the pipe, and I etch it and I apply this cellulose acetate. And when it's dried, then I put it on these glass slides. Or I can, that blue thing, that's a silicone rubber, that can also replicate a surface. And we save a lot of money by doing it this way. There's some limitations. So the in-situ replica, I'm going to call it in-situ replicas. It's called by all sorts of different names. Here's some other ones. They're called in-situ metallography, non-destructive metallography. And this one here, FMR, I didn't even know what that was when I was first asked if I could do it. And like a typical consultant, I said yes. Well, I quickly Googled it to see what FMR was and what I agreed to. But in-situ replicas is probably the better title because we use it for more than microstructures and use it for metrology, scale analysis, fractography. And these last ones, the failure analysis and API 579, then that's for microstructures. So I'm not going to cover the detailed steps on doing an in-situ replica because there's about a half a dozen videos out there right now on YouTube that'll kind of help you with that if you want to learn how to do it. Instead, we'll just give it a brief review of the techniques for in-situ, the applications, that's more important for you as an inspector, limitations, artifacts. Artifacts is just ASTM's nice way of saying that you kind of mucked up when you did the replica. You know, you got some things that may obscure your interpretation. Then call it a defect because this is really an NDE technique. So this one here, we don't have any math or any software we're going to be demonstrating. Well, you do need software, you need your brain, but this is all metallurgy, microstructure, and I think I threw in a phase diagram near the end. So this is a microstructure. What we see over here, all that white area is ferrite. This microstructure seeing here right now is just ferrite and perlite. So microstructure, it's determined by our chemical composition, our heat treatment, our forming, and also in service with temperature and time we got up to. And microstructure determines our mechanical properties and our corrosion resistance. So it's very important. A decent metallurgist can look at a microstructure and determine whether something is fit for service or determine the damage mechanisms. If you're going to start offering this in situ replicas as inspection service, I would say the first thing you have to do is you have to get certified as a welding inspector. At least you're going to get the basic knowledge on, if you're an API or CWB welding inspector, you're not going to get much on microstructures. This book here on the right-hand side is very useful. It's free. It's given to a lot of college students as a kind of first semester required reading. And it'll help you a lot as far as microstructures in carbon and low chromium steel, I should say low chromium heat resistant steels. Very easy to read, and you won't have any problem with that. And that's going to help you a lot if you want to start learning to interpret this. I put that big red arrow there because that points towards something that people thought was graphitization, but you have to have the knowledge on metallurgy to know that this graphitization isn't going to occur at the sort of temperatures we're operating at for this particular pressure vessel. So understanding some microstructures in metallurgy is important if you're going to do this. This is how I do it in the lab. It's called a Buehler HandyMet, and it has rolls of silicon carbide paper going from left to right of different grit size. We do the same thing in the field too. And all I do is I put these samples that have been mounted, and I just go back and forth. There's some water there to remove the grinding particles. And then when I go to the smaller, the finer grit size, then I rotate it 90 degrees. And the reason I'm rotating it 90 degrees is that I'm trying to ensure that I removed all the scratches from the previous step. And we do the same thing in the field. And this is how we do it in the field, except the fact that, instead of a big clunky drill like this, I have a smaller rechargeable one. But we have silicon carbide papers that are adhesive backed, and we put them on these holders, these 3M holders. And I go back and forth 90 degrees on this one. This is a replica that I did. I'm not too proud to say, because when you look at this, I've got scratches that are going at horizontally big scratches, like 240 grit scratches. And you see some vertical scratches too. And those are from the 600 grit. So what's happened is I haven't removed the scratches from that coarser paper. And I'll never get rid of them. This is going to be an artifact on that client's replica. But there's one little area that doesn't look bad. And I think this would be, I still gave it to the client because we had to get it done quickly. And there still was one little particular area where I could answer the client's questions. But scratches are an artifact. Another thing that's an artifact, because we're going to go over a few of these artifacts, is that all these little black particles that you see on this microstructure are refractory dust. So they're abrasive. So I'm trying to polish something down to a mirror finish, and they're falling on the surface, and it's going to give me scratches all over the place. And there's nothing much you can do about that because these particles are suspended in air. So you can't put up a tarp or anything. All it means is that, that's one artifact that you can't prevent. The other one where I just didn't remove the scratches, that was my fault. Well, then when in the field, what I do is then I go to diamond paste, and I apply some diamond paste on this cloth. That one off here to the right looks like a Pringles chip, but that cloth needs to be flattened. And this is going to be another artifact I've had here. We have two different types of cloths shown here. One is kind of this fuzzy one that's gray that kind of looks like it's fur. My cat thinks that these are mice, so it'll attack them whenever it sees them on the floor. But this one with a fuzz is not a good one to use for in situ replicas. The one that looks like it's sitting on a dinner plate is a cloth that is flat. and it gives us better in situ replicas. But we use the cloth with the fuzz, the fur on it, because what it does is if you're in an environment like a fired heater or a boiler where there's some refractory dust, or in the case I was working in a farmer's field on a pipeline, and he was plowing his field, you want something where all those dust particles can kind of hide in all of this fiber and not scratch your surface. So that paper with the fuzz is good for something like this, where you have lots of dust, but it's not good for other things, because otherwise what we get is relief. And relief doesn't mean the job is done, I go for a beer. Relief means I've got this kind of three-dimensional effect here. You see these plateaus. This is a microstructure of just a ferrite, and there's not a big depth of field on our microscopes. And so ideally we want something to be flat. Later on, we're going to look at the idea that we have to look at the grain boundaries to find carbides or voids, and something like this makes it almost impossible. So this is polished with a cloth with nap, and we don't want that. It's only good for those applications where you have lots of dust. The other problem too is that cloth with nap is another artifact that ASTM doesn't like, is we tend to pull out carbides and precipitates and inclusions very easily with that cloth with nap, and then we're left with something like this. You really couldn't tell if that's a crack or whether I pulled out something out of the steel, and now it's going to make interpretation very difficult on that one. So ideally, I have cloth with nap, but I don't use it that much unless it's really dirty outside. So this is what we do. So this is just kind of a side view of looking at the pipe. So I see the bottom one is going from left to right. I got a crack, I got a precipitated, a grain boundary, I got a void. And now what I do is I wet that cellulose acetate, I put it on the surface. And of course, now I'm getting a negative impression of everything that was on that surface. So a crack on the replica, I end up looking at that surface with a blue arrow, comes out looking like a ridge. A precipitate is going to look like a hole. A void is going to look like a bump. And so you have to get kind of used to looking at the reverse image of what you're seeing on the replica. The cameras will reverse it for you, but they don't seem to do a very, very good job of it. And this is an example of cellulose acetate replica off a pipeline steel. They thought there was stress corrosion cracking, and so you're seeing all these lighter areas, those grains are ferrite. The darker areas are pearlite. Of course, we're not seeing any of the microstructure in the pearlite right now, the lamella, but that's a low enough magnification. So when they looked for stress corrosion cracking on the surface, there was nothing. And I suspect what they was not stress corrosion cracking, but I suspect they were laps. Laps are just pushed over metal on the pipe surface. And if you're a pipeline inspector, you probably already know this, but you can just kind of drag your fingernail along the surface. And if it's a lap, it'll catch your fingernail, versus a crack won't. That probably isn't a good way of doing pipeline integrity, but in that case, all those things that we looked at were laps, and they were pretty common in certainly in the older steels. So once we get all this etched, we can look at this at the surface different ways. We can either take that cellulose acetate replica that I talked about, or we can put a microscope right on the piece of metal, or we can use a silicone. Silicone will replicate the microstructure or fracture. Or this last one, Struer's transcopy, is their own kind of proprietary cellulose acetate with a backing on it. In-situ microscopes are really handy, but the unfortunate thing is most of the times I'm working in locations where I can't get the microscope in the area, or I can't get my eye close enough to that microscope. So although they're useful, they just don't turn out to be that good. The other thing too is I can go up to much higher magnification if I take a cellulose acetate than using a microscope I put right on the pipe. And this is the silicone. It's made by different companies here. Those are some of the list of them all. Kind of expensive, and it doesn't do the best of jobs compared to the cellulose acetate, but it's very good for fractures. This is the cellulose acetate. You can see that roll there of film. You can get it also in a sheet. and you wet it with acetone, apply it to the surface that you just got finished polishing and etching. You let it dry for about 10 minutes. You strip it off and put it on these glass slides. And of course, there's kind of a picture frame around the cellulose acetate to hold it flat. This is the Strur's transcopy, and what they do is it's still cellulose acetate, but they have a reflective background on the back to give you better contrast, because that's one of the unfortunate things with cellulose acetate is we have very little contrast because it's clear, and this will help you out a lot. Now, one thing that I do use for is metrology, and it happens quite often. You're out at some place, and once they find out you can do a replica of a surface, they're asking you to measure a shape. And in this particular case, there were some unusual marks on the gear teeth. And sure, you can take a picture of them, but it's a lot easier to apply some of this metrology grade putty or that silicone rubber we just got finished seeing on this gear. You can bring it to the meeting and show people. Admittedly, nobody is going to pay me my hourly rate to go out and take rubber replicas of anything. So this is always part of a much bigger project, like this would be part of a failure analysis. And in this particular case, you know, there was obviously some foreign material that was getting pressed into the gear teeth. But here's some other ones that we have too. This is a metrology grade putty again. So this one up at the top has some unusual circumferential corrosion in the pipe. I haven't figured out what it caused it, but so we're doing the metrology grade putty. We're putting it on that pipe because it's a failure analysis. This one over on the right hand side, what this one was for is there's a defect at that root reinforcement on that weld. And this one over here, they just didn't prepare the weld groove on the inside of the diameter correctly. So now we got that one done. I'm sure if I'm getting asked to do rubber replicas of objects, you probably will too, sooner or later, if you're doing in-situ replicas. So the other one is we use it for is scale analysis. And this is not the particular one I looked at, but I was looking at a waste to energy incinerator, and the corrosion products they're just gorgeous. I mean, they got fantastic colors in them. So on a scale analysis, sometimes normally we would just scrape the surface. That's all you do. You don't have to worry about doing anything fancy. But on this one here, sometimes you have to do something a little bit different. And the reason is if I have a fracture, I don't want to scrape the surface to get that corrosion product off, because now I destroy that fracture. And sometimes for litigation, they won't allow you to scrape the surface either. Strangely enough, they allow you to take a replica off the surface and take that scale off, because that does destroy it too, but they don't seem to think that's destruction. And the other thing too that happens with the cellulose acetate is that if you got a scale on a surface that's very thin, there's not much there, you can wet the cellulose acetate, apply it to the surface and strip it off like this. And that's what you would get, is you would have the corrosion product on that cellulose acetate, and now it's mounted on that slide. Now I can go off and do energy dispersive spectroscopy on it. If the cellulose acetate is thin enough, I can also grind this up and do X-ray diffraction on it. And I got two slides there, because the first one took off most of the scale, and the second one came back just to take off what remained. And this is what I got when I was all finished. Actually, it looks very beautiful, isn't it? Eh? You know, that's the thing about waste to energy incinerators. It's just a witch's breakfast, or witch's brew, as far as what's in these things. And I don't know why it has this unusually attractive blue color, but always in waste energy incinerators. Chlorine is a big problem. We're going to find sodium chlorides, all the metal chlorides. And what happens on these ones is that the deposits that get on these boiler tubes have low melting points, and they got incredibly high corrosion rates. And when they first started making these waste energy incinerators, sometimes up to about 1 inch per year. And of course, on boiler tubes, you know, you won't even get through a year before all the boiler tubes are finished. This is what we found with I don't think we have to go over this one. Of course, you can see how this is really old results, because back when I did this, we didn't have quantitative energy dispersive spectroscopy. It's We just had to compare the heights, and that's all there was on that. As you can see, in waste energy incinerators, the bad actor is chlorine. We get very little sulfur. It's kind of the opposite of a coal-fired boiler. And there was the majority of it, we couldn't determine what it was because there was no, in the atlas of X-ray diffractions, there was nothing to kind of identify what was there. That's just the way it was back then when we first started looking at these. We can always use in-situ replicas for fractography. And this is just fractography means we're looking at the fracture, we're trying to identify the initiation site, trying to identify the damage mode, is it intergranular, transgranular, trying to identify the failure mechanism. And most of the times I would put this right underneath the scanning electron microscope, but sometimes you're not allowed to cut that piece up. This one's nice and small. Sometimes you're not allowed to cut that piece up. It could be a turbine. And so you have to take a replica of the fracture. Other times they're going to do the repair immediately, in which case they don't want you to start cutting up a fracture because they're going to weld over it anyways. So being able to take a fracture, taking an image of the fracture is certainly useful. And you remember we talked about this is how we can either use cellulose acetate or we can use silicone rubber to replicate that fracture. And this is a silicone rubber replica of a fatigue failure. I wasn't allowed to cut this up. I was going to go back for litigation. So I was only able to take a replica with that silicone rubber. It's not that good though. When you look at that, you see this kind of curved marks. Those aren't striations, fatigue striations. Those are beach marks. And that's about as high a magnification as I could get out of this particular brand of silicone rubber. It's not that good. And but there are the other brands of silicone rubber that are going to be more, give you better resolution on this one. But still, just looking at that, I would say it's fatigue. But since it's a litigation, I better have a bit more ammunition than just the fact that it appears to be that way. So we do failure analysis in the field. This is where we use in-situ replicas, and we're going to be looking at microstructures now. So this looks like a bad skin disease, doesn't it, eh? But this is a microstructure off a reinforcing pad that was welded on a pressure vessel here in Alberta. It had cracked in the heat affected zone of the reinforcing pad. And so they wanted to know, what did possibly cause that? The hardness I measured with a Brinell, couldn't do the heat affected zone with tele-Brinellers, but it was like about 260 Brinell, which is way beyond what any pressure vessel steel should be. And although I was never able to find out what this reinforcing pad is, all those little spots that you see there, what they are is iron carbides. And I suspect this is a tool steel. And tool steels have carbon contents up, 0.8% carbon. So if you're a pipeline, working in pipelines, if somebody told you have 0.8% carbon in your pipe, you'd probably be quite concerned about that. That's why they got cracking in the heat affected zone, is their welding procedure was completely inadequate for something of that high carbon content. That's a little bit better picture of it there, but you can see lots of little iron carbide particles there. And you can see also too, is my in-situ replicas pulled up some inclusions in that steel. And the inclusions are, probably manganese sulfide or silicate. And there's a really big one. Oh, sorry, I'm going to go back here. I think there's, nope, I thought I'd kept that one. I didn't. Apologize. So this is going to be a problem. Remember, we were talking about the cloth with nap. If I start pulling out too many things out of the surface, it's going to make it very difficult to interpret the microstructure. This one here, things are so big that I would never get worried that this is something, a creep void or something like that. It's we got something else going on there. I put this one in here as because if you look at this one, this has got all sorts of little spots over it too, eh? And you go back to this one, so does this. But these spots here and this one, it's different. This is an artifact. And you have to be able to just look at that and just say, okay, I mucked up there. What happens is the diamond paste I polish with is oil-based. And the only way you're going to get that off the surface that you're grinding on and polishing is you have to use dish soap. You can't use hand soap or anything like that. Dish soap will take off the oil. If you try something else, if you try ethanol or methanol or some sort of solvent, that oil, all it does is form little balls of oil on your surface, and it gets onto your replica. So it looks like this thing is covered with iron carbides when really it's just drops of oil. So one of the limitations of in situ replicas is it's just that we're looking at the top surface, and almost all the atlases of microstructures that you'll find in pictures, they look on the side view. So, oh, here you got a big stack of pancakes. Looking at it from the side looks pretty good, actually. But you look at it from the top, and it looks pretty ho-hum, doesn't it? So it depends on how you, and the microstructures are the same way. So here's what they've done is they just assembled a three-dimensional view. This is, of course, the rolling, the one on the top there that's the surface we look at. And the other two are what we would do is if we cut it up in the lab. And as you can see, the grains are much larger on the surface. We seem to, it's not, the perlite isn't distributed very uniformly. And you have to kind of get used to that's just not that's just typical microstructure that you're going to get. Like this one here, that's the top surface. And we got this one big area of perlite here up in the left-hand corner, almost none down in the right-hand corner. And this is when I did it with a cross section in the lab. I mean, it doesn't look, those two don't look anything like each other. It's the differences between the X and Y planes and the Z planes are much less for pipelines because you just don't have a lot of carbon in it. And I suspect it'd be much less for a plate that's maybe been normalized. Well, one other application that we end up using this one for is for in API 579 part 3. That's when they talk about brittle fractures of pressure vessels. And the problem we have is that some of these old pressure vessels back in the 80s and 70s, well, they're still working. And the unfortunate problem is they were made out of rim steel. The old ASME codes didn't have any impact toughness exemption in them like they do now. You could use any carbon steel you wanted down to minus 20 degrees Fahrenheit on any thickness. And so now they're susceptible to a brittle fracture. Now, mind you, if you've had a pressure vessel that's been operating without any problems for 40 or 50 years, you might argue that, it's really not an issue. All that means is that you're loading it very slowly, not maybe deliberately, but that's the way you've operated it. So I had a client that wanted to know if his pressure vessel, which was just about 50 years old, was made out of rim steel. Rim steel, so after it comes out of the basic, I should say, if it comes out of the open hearth furnace, it's to the carbon and silicon content we want and the manganese content, but it's saturated with oxygen. Now we have to get rid of the oxygen somehow. Oxygen gives us really bad impact toughness, right? So one way to get rid of that impact toughness, I should say one way to get rid of the oxygen is we allow the steel to rim. So we allow the carbon and oxygen to react. And what we get is a thin rim or layer of almost pure ferrite at the boundary of the ingot, at the surface of the ingot where it meets the mold. And that's called rimming, and that's called a rim steel. The unfortunate problem with that is that there's still way too much oxygen left in that steel. And the impact toughness, the transition temperature for that steel is probably going to be up above the room temperature. So it's a disaster waiting to happen. Even at minus 20 Fahrenheit, it'll work fine. You just have to load it slowly. You don't want to have any stress concentrators there. And so it's important for clients to know, does he have rim steel? That's what API is trying to find out, and just saying, okay, if you do, then you want to operate it correctly so that you never get into a brittle fracture. Because when that does occur, the brittle fracture is so quick, you can't inspect it for the brittle fractures. The fractures are too fast. So rim steels, what they have is that really thick layer of pure ferrite, almost pure ferrite on the surface. And when it gets rolled into a plate, all it happens is that thick layer gets just squished down. It's all in proportion. So if you get a plate, you'll have a layer of almost pure ferrite on the surface, and that'll still persist even on the plate. And that's what we've got here. So I took an in situ replica of this pressure vessel. That's what we see here. That whole surface, all we're seeing here is grains of ferrite, nothing at all, nothing else. Now I ground off about 10 thousandths of an inch because I want to make sure that this is not due to decarburization. And you will get some decarburization at the steel mill, but once you go down to that depth, no, this is a rim steel. And the only thing he has to be aware of now is that client is, to operate it correctly. It means the steel is susceptible to a brittle fracture. You load it slowly. Maybe you don't do a hydro test at low temperatures. Maybe you have some sort of management of change notice so that people understand what the problems are with that vessel, and you'll be fine. I put this one in here only because this is another of the same one. And first of all, we were getting that relief. Remember, we talked about that relief being sometimes caused by the cloth. The other reason, too, is that you get that relief in surfaces that have almost no carbides in them. And I don't understand what actually is happening there. So getting relief on a decarbonized surface is quite common. You see those kind of wavy lines that you see on there. Well, they're strain lines, or sometimes called strain markings. And what they mean is that that pressure vessel was cold rolled and was never heat treated. And, considering that vessel, the age of that vessel, that's probably pretty common too. These are just some artifacts, bubbles. Now that, believe it or not, is sweat from my fingers. And it looks kind of lamellar. You might even kind of think it looks like a microstructure. So you have to be careful when you touch these slides that you don't get your fingerprints all over them, because maybe you might get that confused with, or it's going to obscure your microstructures anyways. The green filter, the only reason is because I had a green filter on the microscope. These are some more bubbles that, that one back here, that's an artifact, of course. So that just means being careful that you don't touch the slides with your fingers. Here's another artifact. All those little bubbles there are bubbles in the methanol. I don't know what it is, but methanol does not dry that well on metal surfaces. And it leaves kind of, I don't know what the impurity is in it, but in this particular case, that artifact, the easy way to get around it is just switch to ethanol. Here's some more bubbles. And we get a lot of bubbles actually on in-situ replicas, and clients seem to get quite annoyed at them. But the thing is that when you apply the acetone to the cellulose acetate, sometimes you apply too much. So maybe sometimes you haven't let it dry enough, and you have to reach way over to apply it to the surface that you polished. It's not right in front of you, and so sometimes you do get bubbles on these surfaces, and the only thing you can do is take another replica if there's that many of them, or maybe just move to another area on that slide where we don't have bubbles. This one is, so if we're, lots of times this is one of taken at high temperature. In fired heaters, they're susceptible, if they're carbon steel, they're susceptible to graphitization. And graphitization just means that the perlite is being converted into graphite, and because that's the stable phase. And you can have a lot of graphitization in your pipe before it's a problem. But what sometimes happens is that we get it concentrating close to the heat affected zone of a weld. And now that's bad. So if you're a client and you find graphitization, you probably want to look at your welds. Unfortunately, you probably won't see it with an in-situ replica at the weld, but you can see it here. Those things that look like, well, they look like, I don't know, like squash bugs here, those black ones. Those are graphite nodules. And this has been at high temperature. And so what's happened now is all that iron carbide is converted into graphite. And those areas where I pointed the arrows, that's mechanical damage. That's another artifact. What's happened here is that, I just didn't grind long enough to remove the mechanical damage that I get. I still gave it to the client because really all he wanted to know was, do I have graphitization? The fact that you get those little bands, and you can see how those little bands go from one grain boundary to the other. And this is what happens is we're just looking at the side view, is that underneath all those scratches is that green band that's been plastically deformed. And if we don't take the scratches off and that green band, we end up getting that grinding damage that you saw in that previous one. So if we grind off all the scratches, there still is plastically deformed layers underneath. And so we have to grind a little bit longer to get rid of that. But you're always under pressure to get things done quickly. The next one I'm going to go over, which is probably the one that most people are interested in, is creep damage assessments. So all those blue arrows, those are creep voids at grain boundaries. So this is the beginning of the damage on a material for creep. In-situ replicas are the only method of NDE method of finding the early stages of creep damage. Now, there's a lot of people out there that say it doesn't work. So you can see all those little balls at the end at the grain boundaries. What each one of them are is that they're a void. So they're not a particle, they're actually a little void. And you see, so I got 3 pointed around, and they're occurring on the grain boundaries that are at right angles to the principal stress. In this case, the hoop stress. So the hoop stress is going vertically. And this one, the whole idea of looking for creep voids and creep fissures was all based upon, this is a good paper, try and get this one. This is kind of the beginnings of this one, is this rest life estimation by Neubauer and Waddell. And what they found is they spent years looking at alloys, low alloys, at coal-fired power plants. And what they found is that when creep damage starts to occur, creep only occurs at high temperature, of course, is that the first thing that happens is you get these isolated voids occurring, and then they start aligning themselves. And then they become something called microcracks, because they're only about the size of a grain. And then they're macro cracks. At that point, you can pick them up with conventional NDE. And that's what we had back here, is that those blue arrows are pointing to, in that one case, the left-hand side, it's pointing to an isolated creep void. And these other ones we're seeing, they're starting to align. So that's a later stage of creep that's occurring there. And now the method that they came up with at that point is, it's good because you can do this in the field. So you can do it on if you get a modest quality microscope, you can do this on scaffolding right in the field, versus some of the other methods you're going to have to end up doing quantitative metallography, and that's going to have to be done back in the lab. But this is the beauty of this method, and why after pretty close to 40 years it's still being used. So they came up with different damage categories, A, B, C, and D, and it doesn't tell you how the remaining life is. It just tells you what you have to do for your next inspection. So if you had isolated creep voids, like A, what you would do is you would inspect again in 3 years. And if they're starting to get aligned, then you'd inspect again in 1.5 to 2 years. So if we go back to that one there, that one over that, if all we found was those things like that on that left-hand side, you'd inspect in 3 years. That one in the center, yeah, every 1.5 years, 1 to 1.5 years, you'd go back and re-inspect that boiler tube. And C means you can probably run for a little while. You're going to have these micro cracks about the size of a grain. You can probably run for half a year before you have to do your repair. So before I said it's the only method, I put that big but there. It's the only method to find creep life in early stages of creep life, but it doesn't work all the time. The replicas are small compared to the pressure equipment. If you haven't taken the replica in the right location, you're wasting your time. You're getting the wrong results. So that means that somebody has to be able to give you information where things have failed in the past, maybe where they found high temperatures, maybe they did a finite element analysis and determined that this was a more applicable area. The other thing that's problem with doing these in situ replicas for creep is that these higher heat resisting alloys like the 9% chromium, they don't develop creep voids at the surface until later on in their life. So that this method that we just talked about, doesn't work for them. And the other thing it doesn't work for is like if you have a big welding defect inside your piping, it's a stress concentrator, and the creep damage will start on the inside before it will be detected on the outside. So we have to hope that there's nothing on the inside that gives us that problems. The other problem is that you may not be used to looking at what voids look like, and that's always an issue. And your technique or your equipment maybe just isn't good enough. So when we look back on this one here, once again, if you looked at that, you might say carbides go to the grain boundary also too. So when I'm looking at those things, am I looking at a creep void, or am I looking at a carbide at the grain boundary? you have to be able to determine that. And the only way to do that is you raise and lower your stage on the microscope, rather high magnifications, maybe 600 or 800 times magnification. And you look for what comes into focus first. It's a pretty tedious way of doing it. If you have an electron microscope, it's a lot easier. And because what you're doing now is that objective lens, you're lowering the stage, and so it's out of focus. And then you raise the stage, and the first things that come into focus are going to be voids, because remember, voids are kind of we're looking at the negative image of what they are. So a void we'd see first, and then later on we'd see the matrix. So that's the only way you can kind of determine something is a creep void. The other problem too, the reason why people can't find these things is that if you do one polish and etch, which is normally what we all do in the lab, it won't detect these things. What you have to do is several polish and etches, polish, etch, polish, etch, polish, etch. And what's happening now is that it depends. Some people said you're removing smeared metal that kind of covers over those very small voids. And now those voids all of a sudden start to pop up. So if you've not found them, that's maybe something to look at, is that your polishing technique. And I wouldn't etch for a very long time either, because you saw the size of those. I'm going to go back here. You saw the size of those particles. So if I etch for a longer time, those grain boundaries get wider, and now I'm not going to be able to see those voids. So you have to do a very light etch, which normally we don't do, but you want that to show up those voids. And the other thing too is to get this method to work is you can use a better microscope. That's always important, but you're out in the field on a scaffold, so you're probably not going to have a good quality microscope. And the other thing is you can use some thinner cellulose acetate. It's going to give you better resolution. The last one is spending more money. That just means maybe taking it to the electron microscope or sputter coating it. And the last slide I'm just going to go over is that, sometimes maybe the problem is these replicas aren't flat, and that gives you a big issue, because either you're going to have to do a lot of image stacking, or you're not going to be able to do quantitative metallography that easily. So you want to keep these things flat as much as possible. So when you get the tape, I just flatten it under some books. When you apply it to the surface, you don't want it to fall off, otherwise it'll just shrivel up like a shrimp chip. You want to apply the acetone kind of uniformly, keep the replicas kind of sharp, and you can use Z stacking software. It's just kind of time consuming. And then that's probably about it. I think we've kind of gone to the end.
That was very good. Thank you very much. We're going to move into our live Q&A channel at this point. There's a QA button at the bottom of your Zoom client on there that will allow you to ask questions directly. I know a lot of people are asking it within the chat, so I'll try and go through that. But the Q&A portion is a lot nicer way to answer that. So maybe to start off with, so Bruce, you showed a good example of this whole process being used to find stress corrosion cracking in pipelines. Do you see a lot of this use of process on pipelines? And then when you're doing it, what do you typically hope to learn out of that?
Well, of course, so then what's going to happen then, Brett, is the cracks are either going to be intergranular or transgranular for stress corrosion cracking. And I find that a lot of times what's happening on the older pipelines, it's not cracking at all. It's laps from the steel mill, and they show up looking like cracks because they're doing fluorescent magnetic particle inspection. They stand out unbelievably well. And the only way you can determine if they're a lap, sorry, is using that fingernail, which isn't a very good way of doing anything as far as pipeline integrity. I think what I find now is that people aren't doing it as much. And maybe it's just new inspectors, because I think an older inspector would just say, yeah, sure, it's just a lap, and leave it like that. So it doesn't come up as much as it used to. But I would say 10 years ago, yeah, it was very common.
Awesome. Thanks for that. A question from the audience. So you had a slide back that kind of showed fatigue on a turbine blade. Do you remember what the mag was on that rubber replica for that blade?
Yeah, it wasn't very high. I think it might have been like 100 or 200 times magnification. It was really, really low. And the trouble is the silicone rubber that I was using, it just doesn't have the resolution. In fact, even the manufacturer says it's not that good. I would say if you're going to do something like that, you want to replicate a fracture, I would go to one of the other ones that were listed on that slide. That one was a Buehler replicating media, I think it said, and some of the other ones are better. I had heard that the one called Microset is supposed to be pretty good as far as giving better resolution, but yeah, that one is only like maybe 100 or 200 times magnification.
You say only 1 to 200. It's mind-blowing how detailed you get out of that. Somebody who doesn't look at, grains and steel or anything else like that on a regular basis. It's quite interesting. So you also had, during one slide on there, you were showing a slide right there of some grade 70 steel, and they had like these like little micro lines across on it. Is that known as banded microstructure? And if not, can you explain what that is?
Yeah, that's right, because we were looking at that one where we had the 3 planes, like, and they assembled all 3 X, Y, and Z planes, and you're right, that one is a banded microstructure. And from you guys for pipelines and that, because those bands were always a little bit more susceptible, I think, for sulfide stress cracking and Hick. And so yes, the manganese is kind of segregated to those areas, and so now we tend to get more perlite in that area. I don't think you can ever get rid of them as far as rolling or heat treatment, conventional ones anyways. But yeah, that's you don't see them quite, just an answer to that, you don't see them quite as much anymore. And I suspect the reason is that our carbon contents are decreasing in all our pipeline steels and all our pressure vessel steels, so they're not as distinct as they used to be. An old steel, though, yeah, they'll be quite prominent.
Awesome. Thanks for the insight. What's your opinion of using, in-situ metallography for 885F brittlement damage mechanism verification?
I don't think you'll see it. And the reason is because the microstructure is so fine at that point. I don't even think I could see it in the lab with a conventional light microscope. I think I would have to end up going to even something like the electron microscope. So I don't think you'll see it at all with in-situ replicas anyways.
So when you're looking at the scale removal process, other than creating, a beautiful work of art that the slide there described, which I thought was quite amusing. When you're looking at that, what conclusions do you hope to draw from this process? And then how should an operator adapt to that analysis?
Well, in that case there, what happened was they had a fracture, and they wouldn't allow me to scrape that product, this corrosion product, off there. And the reason is because that fracture, they wanted to put it underneath the electron microscope. And if I scrape it with a dental pick, it leaves marks on the surface that they can see with the electron microscope. I mean, it seems odd that you have to be gentle with a piece of steel, but yes, you do for a fracture. And so when I take that scale off, what I'm trying to get on that one is I'm going to take that scale, that work of art, as you said, and I'm going to end up taking that, and I can do EDS right on it. And but I have to coat it first, because otherwise the electron beam is just going to build up charge on that. But once I do that, I can do energy dispersive spectroscopy. I can find all the elements that are in there, and that one there for what I was looking for was it's chlorine is the bad component in waste to energy boilers. And then we also did X-ray diffraction. We had to grind up that cellulose acetate. It's not crystalline, so it doesn't show up. But in that case, for the X-ray diffraction, we didn't learn a lot. We couldn't identify the spectra coming off for the X-ray diffraction. That was back in the 90s. And now, of course, it's all computerized, and you can probably do a much better search than you could back then. But I think like about 60% of it was unknown. They thought it was some type of chloride, but that's about it.
Do you remember what they did to adapt? Did they change?
Oh, yeah.
What was going in, or?
Yeah. So what you have to do on that one then, Brett, is that when they first started developing these waste energy incinerators, well, boilers, I should say, they made them exactly like as if there was a coal-fired plant, which is a big mistake. And both of them generate lots of ash. So I guess they thought, well, it's probably going to be similar. And so they used the same alloys as they used in coal-fired boilers. But, you know, they got incredibly high corrosion rates. So the only thing they could do, aside from going for more exotic materials, is they drop the metal temperature down. And so if you drop your metal temperature down, you know, you can get at the point where all those, that ash isn't fluid. It's just going to stay there and it won't cause that, just because once it becomes fluid and flows off the pipe, then of course it exposes that pipe to the gases again. And now you get that corrosion being pretty quick. So they drop their metal temperatures down, which unfortunately dropped their steam temperatures down. And some of these waste energy boilers were operating like maybe 10% efficiency, which is really bad because, you know, good coal, even a good modest coal-fired boiler, you know, probably 30–35%. Doesn't sound that good, but, you know, waste energy boilers were pretty bad. That's how they got around it rather than going to more exotic alloys, which would be a solution.
No,
Fair enough.
No, thanks for explaining that a little bit better. So we're going to go to our last question here that we have time. It's already 1 o'clock here. So thanks everybody for all the great questions you've submitted on it. I believe we were able to get to almost all of them on here. But so considering the acetate is flexible, how important is the flatness of the area to be replicated as opposed to metal samples where it's extremely important in order to avoid those blurred micrographs?
Yeah, you can actually replicate a, you know, really odd shape sometimes with this cellulose acetate. So you can do a valve, for example, and sometimes valves have double curvatures on them. So they're not just round, they've got another curvature on it. And the cellulose acetate, if you get the thin one, you can apply it to the surface and it'll conform. And which is nice because if you didn't have that, it would be very difficult to look at that with a microscope if you put that in situ microscope on it, because everything it won't be in focus. So that's the nice thing with in situ replicas. You can do it on a shaft, for example, and even if it's a small diameter shaft, you can replicate the whole surface and that cellulose acetate will conform to that. And you won't have to do image stacking on that one because you just peel it off and then you just kind of lie it flat on the microscope slide, and now you won't have to do image stacking. But you'll find though you pretty much always have to do some image stacking to get a decent picture because the replica just doesn't stay flat when we take it.
That's all the time we have for today. Thank you, Bruce. Really, really appreciate you coming down here and giving a great presentation. A lot of really good information and good detail on that. So thanks again. I'm glad we were able to make this happen. So with that, we're going to close things down. Thanks everybody for joining. Thanks to everybody for all the great questions that you provided on here. The video here will be posted to our YouTube channel. So feel free to tune into there to view the presentation again or any other questions we have. Be sure to continue following us on LinkedIn for upcoming presentations that we have here on our webinar series.